Astronomers have just upended what we thought we knew about the universe from the far reaches of space. Our universe spans 93 billion light years, housing over 2 trillion galaxies with enormous structures stretching 4 billion light years across. But you won't believe what new findings have revealed. The universe might actually be 250 times bigger than we can presently observe, and our previous calculations could be off by millions of light years. If you're intrigued by cosmic measurements, do give this a like. Get ready for the mind-blowing size reveal of scientific history. In 1908, Henrietta Swan Leavitt was peering at her photographic plates, completely unaware she was about to upend the understanding of the universe's size. As a human computer at Harvard Observatory, Leavitt noticed something odd about specific stars in the Magellanic Clouds. These stars pulsated with a perfect rhythm, like cosmic lighthouses beaming across impossible distances. Her discovery eventually proved that our galaxy was just a speck in an unfathomably vast space. These stars, known as Cepheid variables, are massive suns that expand and contract in regular cycles. Here's the game-changing insight. The brighter these stars are, the slower they pulse. This allowed astronomers to calculate their actual brightness just by timing their flicker, revealing the scale of billions of stars situated millions of light years beyond the edge of the Milky Way. In 1925, Edwin Hubble built on Leavitt's method to show that the Andromeda Galaxy is 2.5 million light years away from Earth. Suddenly, the known universe expanded from being 100,000 light years across to over 5 million light years in diameter. It was like realizing your backyard held an entire continent. This kicked off a measurement revolution that continues today. Each breakthrough showed that prior size estimates of the universe were laughably small. Our understanding of the universe kept growing, from millions to billions to trillions of light years. Modern telescopes now uncover galaxies so distant, their light began traveling to us when the universe was a mere 300 million years old. These ancient markers emanate from distances so vast they're nearly beyond our comprehension. If the Milky Way were the size of a dinner plate, the observable universe would stretch beyond North America. The kicker? Everything we see might make up less than 4% of what's truly out there. Dark matter and dark energy, forces we scarcely understand, seem to overshadow the cosmic fabric. We're like ants trying to map out a whole planet while perched on a single grain of sand. Cutting-edge instruments indicate our past calculations might yet be wrong. The observable universe could be slightly smaller than we thought, or the actual universe could be hundreds of times bigger than the part we can detect. But before we can fully grasp these unimaginable scales, it's crucial to understand something more fundamental about our spot in this cosmic sea. Each night, when you look up at your bedroom ceiling, you're gazing through more emptiness than the brightest minds once thought could exist in the entire universe. Ancient Greek astronomers believed the cosmos consisted of crystal spheres around Earth, with stars residing just a few thousand miles above us. Aristotle figured the whole universe could fit inside a space about the size of our solar system, a miscalculation by a factor of trillions. Even as late as the early 1900s, astronomers thought the Milky Way was the total universe, measuring about 30,000 light years across, which seemed immense back then. They assumed all existence was smaller than the distance to our nearest galaxies. Just like your bedroom ceiling sits about 8 feet above you, containing the same proportion of emptiness as the space between galaxies in our observable universe. Imagine shrinking the universe down so that galaxies were the size of marbles. In that case, they'd be about 20 feet apart. It's almost like your bedroom mirrors cosmic spacing. This concept sheds light on why ancient astronomers miscalculated the vastness of space. They could spot stars with their eyes alone, leading them to think the stellar sphere was nearby. They were unaware of the massive expanses of almost empty space separating star systems. The game changer came when astronomers managed to use a method called parallax to measure the distance to a single star. Think of it like closing one eye and then the other, watching how nearby things seem to shift against distant backgrounds. Earth's movement around the Sun offers a 600 million mile baseline for these calculations. In 1838, Friedrich Bessel determined that the star 61 Cygni is 11 light-years away from us. That one measurement hinted at more empty space than ancient thinkers ever imagined. They thought one star was close enough to practically touch, but in reality, it was further away than their whole estimate for the size of everything. Nowadays, we understand that the observable universe holds about 10 to the 82nd power of atoms scattered throughout a sphere 93 billion light-years across. If you took all those atoms and spread them evenly, an atom would be about 3 feet from its nearest neighbor. Space is mostly empty, dotted with rare patches of matter. This emptiness is one of the most mind-bending features of cosmic scale. When gazing at a starry night, you're looking at a tightly packed field of material. Viewing in the direction of the galactic center, you see thousands of stars all at once. Yet the distances between them are so immense that light takes years to travel from one to another. But even that view doesn't quite convey the oddity of cosmic measurements. The very tools astronomers use to assess these distances highlight something almost unimaginable about space and time. Take the James Webb Space Telescope, for instance. It captured images of galaxies that shouldn't have existed yet because the universe wasn't old enough. Situated 1 million miles from Earth at a gravitational balance point, its 21-foot wide mirror captures infrared light that's been traveling over 13 billion years. When astronomers processed its deep field images, they found fully developed galaxies shining just 290 million years after the Big Bang. Here's what's mind-boggling about that discovery. According to cosmic evolution, galaxies this old shouldn't have had time to grow so large and structured. It typically takes hundreds of millions of years for gravity to gather materials to form the first massive stars. After that, those stars need to live, explode as supernovae, and scatter elements before new stars and planets can form. It's akin to finding a fully built skyscraper in a city founded last week. The required materials, construction time, and organizational complexity shouldn't fit within the available time. The James Webb Telescope can spot these seemingly impossible galaxies thanks to an oddity in light behavior over cosmic distances. As the universe expands, light waves stretch out like a rubber band being pulled. Light that started as visible blue and white ends up as infrared by the time it gets to us. This stretching or redshift renders distant galaxies invisible to the human eye and optical tools like the Hubble telescope. But James Webb was built to catch this ancient stretched light with its infrared sensors. It spots galaxies whose light has been traveling our way for over 99% of the universe's age. It's so precise that it could pick up the heat signature of a bumblebee buzzing around Jupiter. Such sensitivity allows it to examine individual galaxies that appeared when the universe was only 2% of its current age. These early galaxies are unexpectedly bright, massive, and well-structured for their time in cosmic history. A galaxy known as JD's GS Z14-0, packed with billions of stars, shows it's actively forming new stars. It's amazing how, even when the universe was only about 400 million years old, this galaxy shone brilliantly, hinting at star formation happening way faster than current theories suggest. What's even stranger is that some early galaxies house supermassive black holes, boasting masses similar to millions of suns. Typically, these massive black holes should take hundreds of millions of years to form as they slowly gather matter. Their presence in these young galaxies suggests either black holes form much faster than we thought, or the universe experienced rapid development periods we've yet to comprehend. The James Webb Telescope also found carbon, oxygen, and other heavy elements in galaxies just shy of 500 million years after the Big Bang. This find suggests planets capable of supporting life might have formed billions of years earlier than previously believed. These insights are pushing astronomers to rethink basic beliefs about how quickly cosmic structures come together and grow. Apparently, the early universe was a far busier and faster changing place than old models predicted. However, as intriguing as these revelations about early cosmic history are, they pale compared to the challenge of measuring something that won't stay put long enough to get an accurate size. Think of trying to measure a balloon while it's being inflated continuously, and you'll start to grasp the fundamental issue astronomers face when figuring out the universe's size. Every method we use to measure cosmic distances has to factor in that space itself is expanding while light makes its journey from far-off objects to our telescopes. A galaxy that was 46 billion light-years away when it emitted the light we see now is actually much farther away by the time that light reaches Earth. This expansion creates a brain-teasing paradox. We can see galaxies whose light has been traveling for over 13 billion years, suggesting they should be 13 billion light-years away. Yet, because of cosmic expansion during that time, these galaxies are now roughly 46 billion light-years away. The observable universe stretches to a radius of 46 billion light-years, even though it's just 13.8 billion years old. The expansion rate isn't the same everywhere or at every time, making measurements a real challenge. Edwin Hubble discovered that galaxies farther from us move away faster than those nearby. This concept, known as Hubble's law, demonstrates that cosmic expansion speeds up with distance. A galaxy 2 times farther away recedes at twice the speed. Current readings show space expands at about 70 kilometers for every megaparsec, roughly 3.3 million light-years of distance. This means that 2 points in space that are 3.3 million light-years apart will drift away from each other at 70 kilometers stress due to expansion alone. Across cosmic distances, this expansion can cause galaxies to recede quicker than light speed, creating an observational limit we can never see beyond. No matter how powerful our telescopes become, light from galaxies past this limit is in an impossible race against the expanding universe. This expansion's relentless pace means that galaxies we observe today will eventually vanish from view. Around 2 trillion years from now, cosmic expansion will have carried most galaxies past our observational horizon. Future beings will peer into a nearly empty universe, with only the local group of galaxies left visible. Even more mystifying, the expansion seems to be speeding up due to a mysterious force called dark energy. Making up about 68% of the universe, dark energy pushes galaxies apart with increasing force as the universe ages. It was discovered in 1998 when astronomers studying distant supernovae realized the universe's expansion was quickening rather than slowing as expected. Measuring cosmic distances while accounting for this accelerating expansion requires advanced corrections to our observational data. Astronomers aren't just focused on where a celestial object was when it emitted light. They're also concerned with where it is now, where it'll be when we finally aim our telescopes at it, and how the universe's expansion has influenced the light's journey. The galaxy known as JD's GS Z14-0, currently the most distant one observed, looks to us as it did a mere 290 million years following the Big Bang. By the time its light arrives here on Earth, cosmic expansion has pushed it over 33 billion light-years away. By then, the galaxy has aged another 13.12 billion years. As its light makes its way to our instruments, the ever-shifting universe means that every distance we measure captures a moment in a universe that no longer exists the way we see it. We're always looking at the past, not the present state of far-off cosmic objects. Still, astronomers have pinpointed certain markers in space to accurately measure vast distances as the universe expands. In the Cygnus constellation, a star called 61 Cygni was the first marker to illustrate that the universe has boundaries we can't cross, regardless of how far we travel or how advanced our technology gets. Friedrich Bessel was the one who measured the distance to this unassuming star in 1838, using a method that transformed astronomy and ultimately showed us the edge of what we can observe. His finding of 11 light-years was crucial, marking the start of our real understanding that the universe has a finite observation limit. Bessel used stellar parallax, noting how the star seemed to shift positions as Earth orbited from one side to the other after 6 months. This shift was a mere 1/3 of an arcsec, an incredibly tiny angle comparable to seeing a dime's width from 2 meters away. Yet, this tiny shift opened up our understanding of cosmic scale and the fundamental limits of what we can see. This discovery taught us something profound about the nature of space and light. Since light travels at a constant speed of 186,000 miles per second, there's a maximum distance from which light can reach us within the universe's lifetime. This creates a sphere of visibility with Earth at the center, not because we're unique, but because we're the observers. This visible sphere stretches out to roughly 46 billion light-years in all directions, forming the observable universe with a 93 billion light-year diameter. Beyond this lies the cosmic horizon, an edge as real and unreachable as the horizon on our oceans. No matter how much technology advances, we'll never see past it. The cosmic horizon isn't like Earth's horizon, though. While you can travel towards and uncover new lands on Earth in space, the cosmic horizon marks light that hasn't had time to reach us since the universe was born. Even if we moved faster than light towards this boundary, we'd never catch up to the ever-receding edge of what we can see. What makes this boundary even stranger is that it encircles every observer anywhere in the universe. An alien civilization in the Andromeda Galaxy views its own cosmic horizon centered around them. Their visible universe overlaps with ours, but stretches into places we'll never see. So essentially, every spot in space finds itself at the center of its own observable universe. Recent estimates suggest the universe stretches much farther than what we can see. Statistical analyses of cosmic structures hint that the total universe is at least 250 times larger than its observable part. Some theoretical models even suggest the universe is infinitely large, making the observable portion a teeny-tiny fraction of reality. The cosmic microwave background radiation marks the edge of what we can see through electromagnetic waves. This ancient light emerged around 300,000 years after the Big Bang, when the universe became clear to light. Beyond this light, there's a dark age in the cosmos, unseen to any electromagnetic tools. Gravitational waves bring the exciting potential to peek beyond the cosmic microwave background, possibly showing us events from moments right after the Big Bang. These ripples in space-time move at light speed, but interact far less with matter than electromagnetic waves, promising to bring us glimpses from earlier cosmic times. Realizing that we live in an observable universe of limited bounds, surrounded by cosmic unknowns, has fundamentally changed how astronomers measure distances. Every method now needs to fit within this finite visual reach, calibrated against objects whose light has had enough time to travel to Earth. This observable border guarantees that we might never solve some cosmic puzzles as they lie beyond our grasp. Surprisingly, recent findings indicate that we might have been miscalculating even our observable universe's size, making it smaller by distances that would overshadow whole galaxies. In 2024, astronomers made a discovery that reduced the observable universe by more than 190 billion miles, with evidence from light that's been traveling towards Earth since before the first stars formed. Researchers Nick Tomasello and Paul Halpern developed new algorithms for analyzing cosmic measurements with unprecedented accuracy. Their findings suggest the observable universe has a radius of 45.34 billion light-years instead of the previously accepted 45.66 billion. Although the 320 million light-year difference might seem trivial in cosmic terms, it essentially means removing millions of galaxies the size of the Milky Way from existence. This update stems from more precise measurements concerning the universe's expansion rate since the Big Bang. Earlier calculations used approximations assuming steady cosmic expansion over billions of years. However, in reality, the universe had periods of rapid inflation, followed by gradual expansion, with recent acceleration due to dark energy. Imagine basing the size of a balloon on your overall inflation pace, only to discover you began with quick blows, then moved to steady puffs, and recently started faster inflation again. Previous size estimates assumed inflation was constant. The cosmic microwave background radiation offers the crucial evidence for this revised measurement. This ancient light represents the first radiation traveling freely through space, released when the universe was just 380,000 years old. By studying slight temperature differences in this radiation, astronomers can deduce how much the universe has expanded since then. Advanced satellites like the Planck mission have mapped these temperature shifts with remarkable precision, revealing patterns that provide insights into cosmic expansion history. The data shows the universe expanded more rapidly in its earliest moments than earlier calculations predicted, meaning there was less expansion afterward to reach its current size. This discovery highlights the precision needed for measuring cosmic distances. Though the universe's radius difference is only 0.7%, it changes volume calculations, affecting our understanding of cosmic structure formation, dark matter distribution, and the total galaxy count. The revision also impacts how we calculate future cosmic expansion. A slightly smaller observable universe suggests various scenarios for cosmic structure's ultimate fate over trillions of years. Some models predict galaxies will one day become solitary islands in a growing void, while others offer different timelines for this separation. Even more intriguingly, these new measurements change estimates of how much lies beyond our observable reach. If the observable part is smaller than we thought, and the total universe is a fixed multiple of the observable region, then the actual size of existence might differ from what current theories propose. These precise measurements only became possible through detailed analysis of light from the farthest observable sources. The James Webb Telescope now identifies galaxies that emitted light when the universe was under 5% of its current age. Each observation adds data points to measure cosmic expansion rates across different stages of universal history. Ironically, making the observable universe smaller seems to make it feel denser with intriguing structures. Right now, the same amount of galaxies, stars, and cosmic stuff all fit into a more squeezed space, bumping up the average density of matter and energy across the universe. Being super precise with measurements becomes key, especially when we're trying to compare the galactic neighborhood to the insanely vast structures scattered across the universe. However, these exact calculations seem less impressive next to the jaw-dropping discovery of cosmic structures that make human concepts of large organization seem tiny. Spanning 1.4 billion light-years, the Sloan Great Wall is the biggest known structure in the universe, turning every human-made construction into what feels like a pile of grains. This cosmic giant is made up of galaxies, galaxy groups, and galaxy clusters linked by threads of dark matter and gas, forming a barrier that covers about 1% of the universe's observable diameter. Imagine if the universe shrunk down to Earth scale. The Sloan Great Wall would stretch from New York to LA and back. It was identified thanks to the Sloan Digital Sky Survey, which mapped out millions of galaxies in 3D. When astronomers looked at the galaxy map, they found cosmic matter wasn't just scattered randomly. Instead, the wall contains about 10,000 big galaxies similar to the Milky Way. Envision every star in those galaxies as a sand grain, and you'd have a beach extending from Earth to Mars. The pull from this massive structure even influences galaxy movements over vast stretches of space. The even crazier part? These structures formed much faster in cosmic history than they should have, according to computer simulations. It implies either these cosmic giants came together faster than expected, or we need to rethink how gravity works on these scales. And newer discoveries revealed massive structures like the Hercules Corona Borealis Great Wall, which is over 10 billion light-years wide, about twice Sloan's size. Light itself takes 10 billion years to travel from one end of this structure to the other, nearly 3/4 of the universe's age. These gigantic cosmic formations really make us question how matter organizes on such massive scales. The cosmological principle suggests the universe should look pretty much the same when viewed broadly. Structures stretching billions of light years seem to challenge this, hinting either at a clumpier universe than anticipated or prompting us to update our ideas on cosmic uniformity. Their size also hints at important details about cosmic inflation, the universe's speedy expansion right after the Big Bang. By observing the size and layout of these structures, astronomers gather clues about that period, figuring out how small quantum ripples evolved into these enormous cosmic formations. Thanks to recent findings from the James Webb Telescope, huge structures started forming earlier in the universe's timeline than thought previously. Observations of galaxies from when the universe was under 1 billion years old reveal clues of organized clumping and structures, showing that cosmic building efforts kicked off almost as soon as stars first appeared. These cosmic giants impact galaxy growth and star creation, as galaxies in dense areas go through different changes than those in more empty voids, affecting their shape, size, and star-making activities over billions of years. Discovering these massive structures makes us realize that we've been seriously underestimating the number of individual components that form such colossal constructs. Christopher Conceal originally thought he was just doing a regular galaxy survey with his team when they stumbled upon something big. It turned out that astronomers had massively underestimated the number of galaxies in the observable universe by a whopping factor of 10. They actually found more than 2 trillion galaxies, whereas previous estimates were only around 200 billion. They made this discovery by using deep space images from the Hubble Space Telescope and advanced 3D modeling to spot galaxies too dim to be seen directly. When Conceal's team turned these images into 3D maps, showing how galaxies were spread out through cosmic history, they realized that over 90% of galaxies couldn't be seen with current telescopes. This updated cosmic count means there are at least 10 times more galaxies in the observable universe than there are stars in the Milky Way. If you tried counting these galaxies at 1 per second non-stop, it would take over 63,000 years to finish. The number of stars in these galaxies is so immense, it's 10,000 times more than all the grains of sand on Earth's beaches. The earlier miscount happened because far-off galaxies are much fainter than those nearby. Plus, many of the smaller galaxies from the early universe have merged to form larger ones. When looking into distant space areas, astronomers could only spot the most massive shining galaxies, leaving the numerous smaller and fainter ones below even the most sensitive instruments' capabilities. It's like trying to count all the lights in a city at night from a distance. The glaring streetlights and neon signs are easy to spot, while the millions of house lights, phone screens, and smaller bulbs stay hidden. Those bright lights represent just a sliver of all the light sources in the city. The team used mathematical models to infer these hidden galaxies' existence, noticing that the early universe had far more small, faint galaxies than previously thought. Over time, these small galaxies merged through gravitational interactions, forming the larger systems we see today. This merging explains why there are fewer total galaxies nearby than in distant areas, with the same amount of matter. Our cosmic neighborhood's galaxies are the merged remnants of many smaller systems from billions of years ago. Observing distant space lets us glimpse these original galaxies before they came together. The James Webb Space Telescope has started to spot some of these once-hidden galaxies, confirming predictions from Conceal's statistical work. Its infrared sensors can capture the stretched light from far-off, small galaxies that older telescopes couldn't see. Every new galaxy found represents an entire stellar system with potentially billions of stars and planets. With this updated galaxy count, there are far more potential sites for planets and possibly life than previously imagined. If even a small percentage have planets capable of supporting life, the number of likely habitable worlds skyrockets. This finding also impacts our understanding of cosmic evolution and structure formation. The gravity from 2 trillion galaxies influences how matter moves and clusters together on a grand scale. This additional gravitational force affects the formation of cosmic filaments, galaxy clusters, and other major structures across the universe. Plus, the sheer number of galaxies puts constraints on theories regarding dark matter and dark energy. The way galaxies are distributed and evolve offers clues on how these mysterious universe components shape cosmic structures over billions of years. Yet, counting galaxies is just one facet of understanding the cosmos. The methods astronomers use to measure distances to these myriad galaxies also reveal core principles of measuring anything in a universe where perspective can create large-scale optical illusions. Measuring cosmic distances hinges on a straightforward geometric principle. It was used by ancient Greek mathematicians to figure out Earth's size, and it's so precise that astronomers today use it to chart galaxies billions of light years away. The idea of parallax involves seeing nearby objects appear to shift against distant backgrounds when viewed from different spots. For example, hold your finger at arm's length and look at it with one eye, then the other. You'll notice how your finger seems to leap against the background wall. The closer your finger is to you, the more pronounced the apparent jump. Astronomers utilize Earth's path around the Sun to form a giant parallax baseline. By observing a star's spot, waiting 6 months for Earth to reach the opposite side of its orbit, and then checking the star's spot again, they can see tiny shifts in stellar locations compared to farther stars in the background. Earth's 186 million-mile orbit provides a triangle baseline large enough to precisely measure distances to nearby stars. The first successful stellar parallax measurement was achieved in 1838 when Friedrich Bessel checked out the star 61 Cygni. He noted a parallax angle of just 0.3 arc-seconds, similar to a dime's width seen from 4 meters away. This tiny angle showed that the star was 11 light-years from Earth, illustrating that the universe had way more empty space than folks had thought. Today, parallax measurements are so exact that they're measured in micro-arc-seconds, like the width of a human hair seen from 100 meters away. The European Space Agency's Gaia mission has gauged parallax distances for more than 1 billion stars. With this remarkable precision, it has produced the most detailed 3D map of our galactic neighborhood to date. Parallax forms the initial step of the cosmic distance ladder, a collection of measurement techniques that build upon one another for gauging ever greater distances. Every method has to be calibrated using the preceding one before it can reliably determine the range of farther objects. By pinning down accurate distances to nearby stars, parallax lays the groundwork for all other distance measurements. However, the drawback of parallax is that stellar shifts become barely visible when stars are more than a few thousand light-years away from Earth. Even with space telescopes that get rid of atmospheric distortion, current tech can only measure parallax angles down to about 10 microarcseconds. This equates to a maximum range of around 10,000 light-years, covering less than 10% of the Milky Way's width. Beyond parallax's reach, astronomers turn to standard candles, objects whose true brightness is known based on physical principles or using nearby calibrations. Cepheid variable stars act as great standard candles because their pulsation periods are tied directly to their true brightness. Once you know a Cepheid's true brightness and how bright it seems from Earth, the inverse square law of light helps determine its distance. The cosmic distance ladder has many steps: parallax for nearby stars, Cepheid variables for nearby galaxies, type Ia supernovae for distant galaxies, and redshift measurements for extremely far-off objects in the universe we can observe. Each step introduces more uncertainty, but the overlaps between methods allow astronomers to double-check measurements and spot systematic errors. Improving parallax precision has uncovered errors in previous distance measures that affected the whole cosmic distance ladder. When the Hipparcos mission revised distances to nearby Cepheid variables, it made astronomers recalibrate distances to far-off galaxies and adjust views on the universe's size and expansion rate. The Gaia mission keeps refining parallax figures with unmatched accuracy, offering the most solid base for cosmic distance measures ever achieved. Each boost in parallax precision shakes up the entire distance ladder, influencing how we understand cosmic scale, galaxy evolution, and essential cosmological measurements. These precise geometric measures become crucial for decoding the next set of cosmic distance indicators, the pulsating stars that act as cosmic beacons throughout intergalactic space. When a white dwarf star gathers exactly 1.4 times the mass of our Sun and goes boom with the power of 5 billion suns, it sets the stage for a supernova, a cosmic explosion that's more reliable for measuring distances in space than any tool we've invented. These type Ia supernovae are among the universe's most powerful blasts, briefly shining brighter than galaxies filled with hundreds of billions of stars. Such stellar explosions occur when a white dwarf, the dense core left behind after a sun-like star dies, siphons material from a nearby companion star until it tips over the scale known as the Chandrasekhar limit. This leads to an explosion that's consistently the same thanks to the laws of physics. Once the white dwarf hits 1.4 times the Sun's mass, nuclear fusion kicks off throughout its entirety, annihilating the star in mere seconds and converting a good chunk of its mass into energy, a process that aligns perfectly with Einstein's equation, connecting mass and energy. This regularity makes type Ia supernovae great for measuring cosmic distances. Each type Ia supernova peaks at about the same brightness, equal to 5 billion suns. By observing these explosions in far-off galaxies, astronomers can figure out distances by comparing how bright the supernova looks to how bright it actually is. This method works over massive distances because these supernovae, being so intensely bright, can be spotted in galaxies more than 10 billion light-years away, enabling us to gauge distances across nearly 70% of the observable universe. No other method can reach such daunting lengths with such reliability. In the 1990s, scientists Saul Perlmutter, Brian Schmidt, and Adam Rees used type Ia supernovae to stumble upon one of cosmology's biggest surprises. They thought that the universe's expansion was slowing down due to the galaxy's mutual gravitational pull. To their shock, they found that the universe's expansion was speeding up, pushed along by a mysterious force we now call dark energy. This groundbreaking find earned them the Nobel Prize and changed how we see the universe's history. It's estimated that dark energy makes up about 68% of the universe's overall energy, yet we still have no clue what it really is. We only discovered dark energy through accurate measurements of type Ia supernova distances and their redshifts. Recent supernova surveys have mapped out thousands of these stellar blasts over cosmic time, showing how the universe's expansion has shifted over billions of years. The data show that dark energy's effect has grown stronger as the universe aged, while the gravitational pull of matter has weakened as space expanded. Type Ia supernovae are also vital for calibrating other distance measurement methods. By checking these explosions in galaxies with Cepheid variable stars, astronomers can fine-tune and improve the cosmic distance ladder. Such calibration has revealed systematic errors in earlier distance measurements, leading to sharper determinations of cosmic scales. The James Webb Space Telescope has started to observe type Ia supernovae at never-before-seen distances, even catching bursts from when the universe wasn't even half its current age. These observations add fresh insights into cosmic expansion through the universe's life and aid in testing theories about dark energy. That said, recent observations of these supernovae have unveiled slight differences in explosion traits, complicating their role as perfect cosmic candles. Some type Ia supernovae are a bit brighter or dimmer than expected, requiring tweaks based on the properties of their host galaxies and specific explosion details. These adjustments enhance the accuracy of measurements using these stellar explosions. The realization that such explosions could serve as cosmic measuring sticks opened the door to understanding a whole new class of cosmic timekeepers, known as pulsating variables, with rhythms that span millions of years. For instance, Delta Cephei pulses consistently every 5 days, 12 hours, and 9 minutes, maintaining its cosmic rhythm unchanged for millions of years. About 700 light-years away, in the constellation of Cepheus, there's a star that plays a crucial role in measuring cosmic distances. Known as a Cepheid variable star, it expands and contracts like a heartbeat, with its surface shifting by millions of miles due to internal pressure waves. This pulsation is possible because these stars are in a finely balanced state. In their cores, nuclear fusion creates energy, which then pushes outward, counteracting gravity's pull inward. As the star contracts, it heats up and becomes less transparent, trapping energy and leading to rapid expansion. This process cools the star, making it more transparent again and triggering another contraction. This regular pulsation links directly with the star's intrinsic brightness. Bigger, brighter Cepheids pulsate more slowly than their smaller, dimmer counterparts. For instance, a Cepheid with a 10-day pulsation period is approximately 10 times brighter than one with a 1-day period. This relation serves as a cosmic measuring tool across galaxies. In 1912, Henrietta Swan Leavitt discovered this critical pattern while observing Cepheids in the Small Magellanic Cloud. Her insight allowed astronomers to use the period luminosity relationship to gauge distances to any galaxy housing these stars. Nowadays, measurements of Cepheids can estimate distances with about 5% accuracy across millions of light years. The Hubble Space Telescope has even captured images of Cepheids in galaxies up to 100 million light-years away, essential for fine-tuning methods to measure even farther distances. Each observation takes weeks, tracking the pulsation period and average brightness of these stars. At vast distances, individual Cepheids become faint, making it tough to observe them clearly. Advanced telescopes with high resolution must distinguish a single star's light from that of billions of others in the same galaxy. This meticulous process must avoid interference from nearby stars. Recently, it was found that Cepheid properties change based on their host galaxy's chemical makeup. Stars in metal-rich galaxies pulse somewhat differently from those in metal-poor ones, requiring adjustments to distance calculations based on the galaxy's chemical evolution. These updates have fine-tuned the cosmic distance ladder and decreased measurement uncertainties. The James Webb Space Telescope can observe more distant Cepheids than ever, pushing this method further into the universe. Webb's capability to see in infrared reduces the impact of dust, which can dim Cepheid light and skew distance estimates, allowing for more accurate calibrations of secondary distance indicators used in cosmology. Cepheid studies have led to surprising insights into galaxy structure and evolution. These massive, youthful stars indicate recent star formation and depict the spiral arm structures of faraway galaxies. Their chemical makeup tells us how galaxies have filled their interstellar spaces with heavier elements over billions of years. Long-term observational programs have tracked individual Cepheids over decades, noting tiny changes in their pulsation periods tied to stellar evolution. Some show period shifts of a few seconds annually, marking different phases of post-main sequence development. These stellar clocks have laid the groundwork for one of the most intriguing challenges in modern cosmology: conflicting measurements of cosmic expansion rates. The discrepancy questions our fundamental understanding of physics. The cosmic microwave background radiation offers a glimpse of the universe's early days, contradicting current measurements of space's expansion pace. This enigma poses a crisis potentially reshaping modern cosmology. This ancient light hails from when the universe, around 380,000 years post-Big Bang, first became clear to electromagnetic radiation. Back in those early days, the universe was so blisteringly hot and packed that light couldn't roam freely. But once things cooled down enough for atoms to form, light could finally zip through space unhindered. This ancient light has been journeying for more than 13 billion years, carrying with it a treasure trove of data about how things were back in the day, all encoded in slight variations in temperature across the skies. The Planck satellite did a stellar job mapping these tiny differences, helping scientists figure out some cosmic details with amazing precision. Based on the cosmic microwave background readings, the universe is supposed to be expanding at a speed of 67.4 kilometers per second per megaparsec. To put it more simply, two galaxies, sitting about 3.3 million light-years apart, should be moving away from each other at that speed, thanks to cosmic expansion. But as we zoom in and measure how fast galaxies nearby are actually pulling away from each other, things don't quite match up, pointing to the cosmos speeding up its expansion. To dive deeper into this puzzle, they're fine-tuning local expansion measurements using big shots like the Hubble Space Telescope and the James Webb Space Telescope. The latest data from James Webb has backed up Hubble's findings with even more accuracy, ruling out a lot of potential errors. It seems the tension is genuine. It's not just a miscalculation or a hiccup caused by other cosmic stuff in the way. One thought is that maybe dark energy, the puzzling force pushing the universe to expand faster, has changed how it acts over time. If it was weaker back in the day and got stronger more recently, that might explain why predictions from the early universe don't match up with today's observations. However, the common belief in cosmology is that dark energy's behavior has been steady throughout cosmic history. Some out-there theories suggest tweaking Einstein's gravity laws might account for differences we see on a cosmic scale, a bit like how quantum physics needed tweaks for tiny stuff like atoms. There's another wild theory postulating that there could be unseen types of dark matter or energy playing a role. These could have shaped how the universe evolved, leading to the mismatch between observations from then and now. As they've honed their tools and gathered more data, this discrepancy has become impossible to ignore. Back in the day, measuring the universe's expansion came with a 20% uncertainty, but now the gap stands starkly at 6%. Some folks believe we might just be living in a unique part of the universe where things move along differently. Local oddities in gravity or large-scale structures might make it seem as though expansion's happening faster without needing to rejig basic physics rules. Cracking the Hubble tension mystery might demand radical changes to how we see cosmic evolution, dark energy, or even space and time itself. This little snag with measurements raises big questions about the universe that still need answering. Yet, figuring out these expansion rates means having a solid grasp on the unseen web holding galaxies together across billions of light years. About 27% of the universe is made up of stuff that doesn't emit, absorb, or reflect any kind of light. Without it, galaxies would just drift apart, and the cosmic structures we see wouldn't even exist. Dark matter shows its face only through its gravitational pull on stuff we can see. Galaxies spin way too fast to keep from flying apart if we only count the visible star's gravity. Clusters of galaxies move in ways that suggest there's about 5 times more mass than what we can directly observe. Gravitational lensing, where gravity bends light around huge objects, needs hidden masses to make sense. All these bits of evidence, coming from different observations, point to the same mind-boggling conclusion. Back in the 1970s, Vera Rubin's observations on galaxy rotation revealed something surprising. Stars on the fringes of galaxies were moving way faster than anticipated, if only the stuff we can see was creating gravitational pull. According to Newton's laws, these distant stars should be slowing down or swinging out into space between galaxies. Without considering dark matter, cosmic structure simulations can't accurately depict the vast spread of galaxies. When astronomers try modeling the universe with just normal matter, galaxies don't pop up in the right spots, and the massive filaments we see today just don't form. This cosmic web of dark matter acts like an unseen framework that supports visible matter. Whatever dark matter is made of, its particles only interact through gravity, and sometimes the weak nuclear force. They don't bump into each other or regular matter except through gravity, which allows them to create smooth, stretched-out halos around galaxies. These dark matter halos reach way beyond a galaxy's visible edges, forming gravitational traps that gather ordinary matter and aid star creation. Imagine the Milky Way nestled in a dark matter halo about 600,000 light-years wide, holding roughly 1 trillion solar masses of unseen stuff. When galaxies collide, dark matter shows its traits through gravitational lensing. In galaxy cluster collisions, dark matter sails right through almost untouched, while regular matter gets stripped away thanks to electromagnetic interaction. The infamous bullet cluster demonstrates a clear split between visible matter and lensing effects, offering solid proof of dark matter's presence. Theories suggest a few possible dark matter particles. Weakly interacting massive particles, or WIMPs, are the top contenders. These theoretical particles would have masses similar to atomic nuclei, but only respond to gravity and the weak nuclear force. Despite many years of using more and more sensitive detectors, no WIMPs have been found so far. Other ideas include axions, very light particles potentially existing in huge numbers across the cosmos. Sterile neutrinos, primordial black holes, and exotic particles hinted at by supersymmetry are also possible explanations for dark matter's nature. Dark matter's distribution impacts cosmic structure on every level. Small density shifts in dark matter in the universe's early days grew through gravity, forming the first stellar nurseries. Without dark matter's gravitational backbone, the universe would be just a smooth expanse of hydrogen and helium gas, no galaxies, stars, or planets. Dark matter also plays a role in cosmic expansion, resisting it somewhat with its gravity. While dark energy speeds up cosmic expansion, dark matter's gravity tries to rein it in, affecting how this expansion changes over time. New insights from the James Webb Space Telescope show that big galaxies appeared earlier than expected in cosmic history, suggesting dark matter halos formed quicker than models currently predict, meaning we may need to adjust our understanding of dark matter during structure formation. The unseen cosmic web woven by dark matter connects galaxy clusters over billions of light years with thin filaments of gravity-bound matter. These connections impact the way galaxies evolve by directing gas flows and helping galaxies gather resources for new star generations. Still, this vast, hidden network of dark matter is outshone by the immense void separating these structures. Incredibly empty spaces like the Bootes void, which spans 330 million light-years, challenge our grasp on how matter can spread out on such enormous scales. Yet they hold vital clues to why galaxies exist in the first place. This massive area of nearly empty space is so large that if the Milky Way were placed in its center, you wouldn't be able to see any major nearby galaxies with the naked eye. Only a few small galaxies are dotted throughout this volume, which should ideally host thousands of big stellar systems. It's one of the largest supervoids ever found, earning it the nickname the Great Nothing. Cosmic voids account for about 80% of the universe's volume, but contain just a little over 5% of its matter. These spaces aren't completely empty. They have dark matter, tiny amounts of gas, and the occasional lonely galaxy. Still, their density is just 1/10 of the cosmic average. If you imagine the average universe's density like air, cosmic voids have a density similar to the space between air molecules. Understanding these enormous hollow regions gives us essential clues about how cosmic structure came together post-Big Bang. In the universe's early days, matter was spread out almost evenly. with barely noticeable density bumps, about 1 in 100,000 parts. Over billions of years, gravity exaggerated these tiny differences, pulling matter from some areas and piling it into others. Spots that started a bit denser attracted more stuff, eventually forming the galaxy clusters and filaments we see today. Those less dense regions lost matter to their neighbors, getting emptier over time. The largest voids are places that started with very low density and have been shedding mass for over 13 billion years. This cosmic sorting led to the web-like pattern we see in the universe, with thin strings and sheets of matter separated by vast empty spaces, much like soap foam or Swiss cheese. Dense walls enclose empty pockets, with galaxy superclusters marking dense areas and supervoids filling the gaps in between. Voids play a crucial role in galaxy development, offering low-density environments where galaxies can evolve on their own. Galaxies in voids face less gravitational chaos and fewer galactic bumps than those in busy clusters. This lets void galaxies hold on to more of their original gas and keep making stars at a steady pace over eons. The way cosmic voids expand also helps test Einstein's general relativity and alternative gravity theories. Einstein's equations detail how matter should move out of these areas under gravity, while modified gravity theories suggest different behaviors that precise void expansion measurements could reveal. Recent studies found that voids are not perfectly round or randomly placed, but have favorite alignments and connect through channels of even lower density. This intricate layout offers hints about the inflationary period shortly after the Big Bang, when tiny quantum fluctuations turned into the initial density pattern. With the James Webb Space Telescope, we can now watch galaxies in far-off voids, gaining new understanding of how these isolated systems differ from those in busier spots. Observations from Webb show that void galaxies often have unique traits, like higher star formation rates and unusual chemical makeup compared to those in dense regions. Cosmic voids also tweak how light from faraway objects moves, causing light-bending effects that impact astronomical studies. Photons passing through these low-density zones experience slightly different gravity effects than light traveling through denser areas, creating minor but important effects that must be adjusted for in exact cosmic measurements. These vast empty spaces indicate that the universe's standout features might be defined more by what's missing than what's present, opening up chances to discover ancient galaxies that could upend everything we thought we knew about cosmic evolution. JADA's GS Z14-0 flashes across space like a cosmic enigma, gleaming with light from hundreds of millions of stars formed in an epoch barely old enough for stellar nurseries. We see this galaxy as it was just 290 million years after the Big Bang, when the universe was a mere 2% of its current age. Back in those early cosmic times, we'd expect the universe to be mostly hydrogen and helium gas, with maybe a few early stars making their debut. But the James Webb Telescope images show something quite unexpected: a fully formed galaxy system that's big, bright, and impressively organized. This find shakes up our theories about how fast galaxies can come together. Computer models tell us it should take hundreds of millions of years for a galaxy this size to come together, with matter slowly building up through gravity. Stars would need to form, live their lives, and explode as supernovae, enriching the surrounding gas with heavy elements before more complex systems could emerge, like the one in Jade's GS Z14-0 galaxy. Imagine finding a high-tech skyscraper during a Stone Age dig. The essentials to build something like that just shouldn't have been around back then. Yet, there it stands, needing an explanation for its quick development. Even more intriguing, the galaxy's spectrum shows a surprising amount of carbon, oxygen, and other heavy elements, stuff that's only made inside stars through fusion. These elements require generations of massive stars living, dying, and spreading their materials across space before there's enough to form new stars. The mystery deepens with JD's GS Z14-0 actively forming stars way faster than expected for such an early time. It seems to be churning out stars at a speed that should have used up its gas in a few 100 million years. This raises questions. Did early galaxies have access to much more gas than we think? Or did star formation work more efficiently back then? The galaxy's brightness suggests it's packed with billions of stars in a small space. This density hints that galaxies were already merging and interacting a few 100 million years post-Big Bang, implying smaller systems had been forming and interacting gravitationally. Recent discoveries have uncovered tens of similar ancient galaxies that challenge established cosmic timelines. Each one seems to reset the clock on when complex galaxies first appeared, indicating the early universe was more active and evolving faster than we once assumed. The appearance of these impossible galaxies is making astronomers rethink basic ideas about cosmic inflation, dark matter, and star formation in those early environments. Some theories suggest dark matter clumped together earlier, creating strong gravitational wells for quick galaxy formation. Others propose that the first stars were huge and burned through their fuel fast, pumping out heavy elements quicker than our usual models show. These so-called population 3 stars might have spread processed materials throughout the universe faster than we've previously thought. With the James Webb Telescope spotting galaxies from even earlier times, it's becoming clear that complex structures started forming almost as soon as the universe became transparent. These results suggest the Dark Ages morphed into the Age of Galaxies much quicker and more intensely than anyone guessed. But even these ancient galaxies can't compare to recent findings about the ultimate limits on how fast any cosmic structure can grow. Back in 1980, Alan Guth was tackling an entirely different question when he stumbled upon the idea that the universe had a growth spurt so fast it nearly defied physics. Guth was investigating why space is so flat and smooth across huge distances, a cosmic puzzle that just kept deepening. The Big Bang theory suggested that space should have a curved shape with random bumps left by its explosive beginnings. Guth figured out that if, right after its birth, the universe expanded super quickly, this thing called cosmic inflation could smooth those bumps out and make space flat by stretching it. During that inflation period, space grew faster than the speed of light. Imagine something smaller than a proton ballooning to the size of a grapefruit in less time than it takes light to zip across an atomic nucleus. That's the ultimate speed limit for how fast the universe can grow. During this wild expansion, the universe doubled in size every 10 to the power of 37 seconds. To give you an idea, if inflation went on for just 1 second at that rate, an area the size of a proton would explode to a size bigger than the universe we can see today. This quick growth phase solved a bunch of cosmic mysteries in one go. It helped explain why space looks flat instead of curved, why the cosmic microwave background radiation is almost the same temperature everywhere, and why we don't see weird leftovers like magnetic monopoles from the Big Bang. But it also raised new questions about how cosmic structures like galaxies and galaxy clusters formed. After all, if space stretched out so much that all bumps were ironed out, how did all these stars and galaxies come to be? The answer lies with the crazy world of quantum mechanics. During inflation, tiny quantum fluctuations happened, and they got stretched into big density variations across space. These became the seeds that grew into all the cosmic structures we see today. Galaxy clusters and cosmic voids can be traced back to quantum events from when the universe was teeny tiny. Observations of cosmic microwave background radiation show small temperature differences all over the sky, a perfect match for what the theories say about inflation. This gives solid proof that this turbocharged expansion really happened. The discovery of cosmic inflation also set hard limits on how fast any physical process can go. Even in the wildest imaginable conditions, cosmic expansion can't go faster than the rules set by quantum mechanics and general relativity. These rules suggest there's a roof on how speedily any cosmic structure can form or change. Recently, scientists using gravitational wave detectors have been hunting for signs of cosmic inflation in patterns of ancient light. If inflation happened as predicted, it should have created gravitational waves that left noticeable traces in the cosmic microwave background. Detecting these would provide direct evidence for inflation and clues about the universe's first moments. The James Webb Space Telescope, with its observations of early galaxies, adds another layer of checks on inflationary theory. If inflation is right, the setup and qualities of the first galaxies should fit the predicted outcomes of those quantum bumps getting a boost back then. Some theories suggest the universe might have had multiple rounds of inflation or varying rates of it across time. These ideas could explain why early galaxies formed faster than standard models thought they would. The speed limit found through studying inflation applies not just to cosmic expansion, but also to all extreme condition physics. Understanding these basic boundaries is now key to making sense of the largest cosmic structures. To travel across the Hercules Corona Borealis Great Wall at light speed would take 10 billion years, which is more than twice the age of our solar system. This enormous cosmic structure is the biggest known in the universe, stretching some 10 billion light-years from end to end. The structure includes galaxy clusters, superclusters, and linking filaments arranged like walls, spreading across about 10% of the observable universe's width. Scientists made this finding while mapping gamma-ray bursts, which are the universe's most powerful explosions. These bursts shine as brightly as 1 billion suns for a brief moment, making them visible over vast distances. When astronomers mapped out thousands of these gamma-ray bursts in 3D space, they noticed that these bursts didn't scatter randomly. Instead, they aligned with huge cosmic structures known as the Great Walls. These came into existence after the Big Bang. With gravity limited by the speed of light, there's just no way it could arrange material over 10 billion light-years in the universe's 13.8 billion year duration. The scale is too big to be solely explained by gravitational collapse. The enormity of the Great Walls is even more staggering from a human perspective. If you shrank the whole observable universe down to Earth's size, this structure would stretch from the North Pole to the South Pole and back. It holds the mass of hundreds of thousands of galaxy clusters, each with thousands of individual galaxies. Computer models so far can't replicate structures this size based on standard cosmic evolution frameworks. These simulations can form galaxy filaments and walls stretching hundreds of millions of light years, but near 10 billion light-year formations are scarce in these models. This hints that we might be missing something in early cosmic conditions, or that there are other forces at play. One theory suggests changes to how we think dark matter interacted in the early universe. If dark matter reacted more strongly with itself, or regular matter in the first billion years post-Big Bang, structures might have developed faster than our models predict. Another idea is that cosmic inflation may have led to bigger initial fluctuations in density than we thought. If these early seeds of structure were large right after inflation ended, they could have grown into immense formations more easily as gravity took over. The discovery also impacts our understanding of the universe's total matter. Structures this huge hold vast amounts of dark and regular matter that affect cosmic inventory calculations. The gravity from these formations changes the motion of nearby galaxies across billions of light years. With next-generation telescopes, even larger structures might be discovered. Tools like the James Webb Space Telescope and other large upcoming telescopes could find the farthest galaxy clusters and filaments, mapping out cosmic architecture in even bigger areas of space. The presence of walls reaching 10 billion light-years suggests that cosmic structures span the largest observable scales, leading to big questions about what lies beyond what we can see. Yet, there's a puzzle about distance and time in our expanding universe. When astronomers view galaxy MAX 149 JD, located 13.2 billion light-years away, they see light that left when the universe was only 500 million years old. Every astronomical observation is like a journey into the universe's past. Looking further into space means seeing deeper into the past, since light travels at a fixed speed and needs time to traverse cosmic distances. Light from the sun takes about 8 minutes to get to Earth, so we're always seeing it as it was 8 minutes earlier. Light from the next closest star, Proxima Centauri, takes 4 years to reach us. When we look at this star, we see it as it was 4 years ago. If it exploded 2 years ago, we won't know until 2 more years pass. This time lag effect becomes more dramatic over cosmic distances. The Andromeda galaxy we see now reflects what it looked like 2.5 million years ago, back when early humans were just starting to use stone tools. The light we receive from Andromeda began its journey before humans even existed as a species. When we look at distant galaxy clusters, it's like looking at the universe as it was billions of years ago. The universe back then was much younger and denser. The most remote galaxies show us what the universe was like in its early days, when the very first stars and galaxies were forming from basic hydrogen and helium. This cosmic history lets astronomers observe how galaxies, stars, and large structures have changed over time by comparing nearby galaxies to those far away. Researchers can track the changes and evolution of cosmic systems over billions of years. The James Webb Space Telescope benefits from this time travel to study how galaxies formed in the universe's first billion years. Every observation catches ancient light that stores information about conditions and workings from places vastly different from today's universe. But the universe's expansion adds complexity to the relationship between distance and the time we look back. While the light travels to us, space itself has expanded, pushing these distant galaxies even further away by the time their light hits our telescopes. A galaxy 30 billion light-years away, when it emitted its light, is now over 40 billion light-years away due to that expansion. This means the farthest things we can see are not just as far away as their light travel times suggest. Cosmic microwave background radiation has been coming our way for more than 13 billion years, but because of expanding space, the spots that emitted it are now about 46 billion light-years away. The relationship between distance and time also changes based on cosmic expansion history. When expansion slowed, light could travel greater distances within the same time period, but during times of accelerating expansion, light didn't travel as far due to the rapid growth of space. These timing effects create biases that astronomers must consider when they study cosmic surveys. Distant objects appear as they did when the universe was younger and more dynamic, whereas close objects show mature systems. Drawing comparisons requires thorough corrections for both evolutionary changes and cosmic expansion. The speed of light also limits how we can communicate across the universe. If we got a message from an alien civilization in Andromeda, our reply would take another 2 million years to reach them. By then, their civilization might have changed entirely or vanished. This light travel time discovery led to a shocking realization in cosmology. In 1998, two research teams studying distant supernovae came to the same bewildering conclusion. The universe's expansion is accelerating, driven by a mysterious force making up almost 70% of everything. Brian Schmidt's High-Z Supernova Search Team and Saul Perlmutter's Supernova Cosmology Project were conducting surveys to measure how expansion rates might be slowing due to gravity. They expected to see that gravity would slow down the expansion, much like when a thrown ball gets pulled back by Earth's gravity. Instead, both groups found something unexpected. Distant galaxies were moving away faster than their distances suggested. The universe's expansion wasn't slowing. It was speeding up, like pushing a car's accelerator to the max. This result went against all theoretical expectations about the universe's development. Gravity, an attractive force, should pull things together, not apart. And the standard model of particle physics didn't have any explanation for this rapid cosmic expansion. At first, both teams figured they might have messed up somewhere in their measurements. They double-checked how they calculated supernova distances, re-examined their redshift data, and looked for any observational biases that might accidentally suggest acceleration. But even when other research groups ran their own checks, they came up with the same shocking outcome. The universe's expansion was indeed speeding up. To make sense of it, scientists had to account for an entirely unknown aspect of the cosmos, something they named dark energy. This mysterious force appears to have negative pressure, counteracting gravity on a massive scale. Unlike regular matter and energy, dark energy becomes more dominant over time as the universe expands and things get less dense. According to current data, Dark energy makes up about 68% of the universe's overall energy content. Dark matter takes up another 27%. That leaves regular matter, everything made of atoms like stars, planets, and living things, as less than 5% of the cosmic pie. Despite years of research, we still don't really know what dark energy is. Some leading ideas say it might be related to the energy density of empty space, possibly from quantum fluctuations in the vacuum. The problem is, calculations for this vacuum energy density are off by a factor of 10 to the power of 120, making it one of the worst predictions in physics. Other theories suggest tweaking Einstein's general relativity to explain the cosmos's acceleration without needing such mysterious energy. These theories propose gravity might weaken over those immense cosmic distances beyond what Einstein's equations predict. The cosmic acceleration discovery earned a Nobel Prize in Physics in 2011 and reshaped our thoughts about the universe's future. Instead of crashing back together in a big crunch, the universe will keep expanding, leaving galaxies further apart as space itself grows. Observations from the James Webb Space Telescope have backed up the dark energy theory by tracking its effects in the universe's earlier days. The telescope studies supernovas from when the universe was less than half its current age, giving us insights into how dark energy's influence has shifted over billions of years. Various independent measuring methods, like checking supernovas, examining the cosmic microwave background, analyzing galaxy clusters, and studying gravitational lenses, all converge to support the same cosmological model dominated by dark energy and dark matter. This shared evidence from such diverse phenomena strongly reinforces our current grasp of the cosmos. Yet, discovering dark energy has opened up more questions than answers, especially regarding what ancient cosmic radiation can tell us about the universe's ultimate size and shape. The faint glow of ancient light fills every inch of space and harbors secrets about regions of the universe so distant that we'll never see them directly, no matter how advanced our technology gets. This cosmic microwave background radiation is the Big Bang's afterglow, emitted when the universe was 380,000 years old and 1,000 times smaller than it is today. Before this, it was so hot and dense that atoms couldn't form, making the universe opaque like the inside of a star. When things finally cooled enough for electrons and protons to make hydrogen atoms, light could travel freely across vast distances. This recombination led to a burst of light that filled the universe, and today we still detect the stretched remnants of that primeval light as microwaves from every direction in the sky. The temperature shifts in this ancient light might seem minor, just a few hundred thousandths of a degree from one spot to another, but they hold a wealth of information about the universe's structure and development. These fluctuations are traces of sound waves that rippled through the dense plasma before atoms formed. Dig into the detailed cosmic microwave background temperature patterns, and you'll uncover a ton about the universe's shape, makeup, and how it has expanded over time. This data is spot on, showing that space is pretty much flat within the margin of error. We're looking at a universe with about 68% dark energy, 27% dark matter, and just 5% ordinary matter. What's intriguing about this cosmic microwave background is that it sets boundaries on how big the universe is beyond what we can directly eyeball. How these temperature fluctuations behave depends on the universe's curvature and overall size in ways that we can measure, even if the actual boundaries are out of sight. If the universe was finite and smaller than what we can observe, we'd notice repeating patterns in this background light as it bounced around cosmic walls. But since we don't see such repeats, the universe likely stretches way beyond what we can see, hundreds or maybe even thousands of times further. New analyses reckon the universe is at least 250 times larger than the portion we can observe, hinting at a total diameter over 20 trillion light-years. That makes what we can see just a tiny bubble in a staggeringly huge cosmos. The cosmic microwave background also spills secrets about the universe's topology. Basically, the big picture shape and connectivity of space. Different models suggest specific patterns in this ancient light that could tell if the universe goes on forever or has exotic finite shapes. Some theories even imagine space like a twisted donut or pretzel, where moving in one direction long enough might eventually lead you right back to start. The microwave background is the best detector we've got for checking out these wild spatial structures. Super precision measurements from the Planck satellite have captured these ancient light temperature variations like never before, setting the stage for limiting cosmic inflation theories and early universe physics. The findings back inflation scenarios that made the universe vastly bigger than the bit we can observe. There's also info in how this cosmic microwave background light is polarized, carrying bits about the universe's early moments. These details might reveal signs of gravitational waves kicked off during cosmic inflation, giving solid proof of that background expansion boom that set up the universe's big picture structure. In the future, other ground and space missions plan to comb the microwave background with even finer precision, maybe spotting early gravitational wave signs or other cosmic birth signals. These observations might help us figure out if the cosmos goes on infinitely or not, and provide deeper insights into the nature of space and time. This ancient light is like a cosmic courier, bringing messages from far-off reality points we'll never directly see, but which still shape and mold what we can observe. As eye-opening as these cosmic constructions are, they're nothing compared to the jaw-dropping discoveries of gargantuan gravitational giants that test everything we thought possible. Hanging out in the heart of a galaxy, there's TON 6-18, hiding a black hole with a mass of 66 billion suns. This thing is so huge, its event horizon could gobble up our whole solar system with space left for countless more. This colossal black hole flips everything astronomers believed about how such beasts grow. Generally, black holes form when humongous stars collapse, resulting in stellar leftovers, typically just a few times the mass of our sun. But to balloon from that smaller size to billions of solar masses should take hundreds of millions of years of steady munching. Yet TON 6-18's gargantuan black hole is from the early universe when there wasn't enough time for such growth spurts. Its event horizon, the point of no return where nothing escapes, is about 800 billion miles across. Light would need nearly 5 days to journey from one side to the other. If a black hole took over the sun's spot, its event horizon would stretch past Pluto, swallowing up all 8 planets and the whole asteroid belt. Thanks to the James Webb Space Telescope, we've stumbled upon even more mysterious, early supermassive black holes. Some galaxies, seen from times when the universe was under 1 billion years old, already have black holes more massive than 1 billion suns. It's as if these things grew way too fast for the cosmic clock. The real head-scratcher is how black holes chow down on stuff. Even with perfect conditions, there's a cap on how quickly they can gobble up matter, determined by the radiation pushing back from their accretion disks. This so-called Eddington limit puts a roof on their growth spurt speed. But even maxing out, hitting those billion solar mass numbers needs hundreds of millions of years. One theory suggests primordial black holes, birthed straight from the early universe's density quirks rather than collapsing stars, might have started bigger, giving them a growth boost. Other ideas say the first stars, made from just pure hydrogen and helium, were way heftier than today's stars. These population 3 stars could have been hundreds or thousands of solar masses, collapsing into massive black holes that kick-started rapid growth. Supermassive black holes have a gravitational pull reaching far beyond their event horizons, impacting galaxy development across hundreds of thousands of light years. They shape star creation in their home galaxies by heating nearby gas with powerful jets and radiation from their spinning disks. Gravitational wave finders have spotted black holes merging, showing they can team up to make even bigger beasts. When 2 galaxies with supermassive black holes collide, their central black holes end up merging, unleashing massive energy through gravitational waves that ripple across space-time itself. These colossal black holes also serve as testing grounds for general relativity under extreme conditions. Near their event horizons, gravity gets so intense that space and time warp drastically, creating phenomena beyond human experience. Matter falling into these giants undergoes spaghettification, getting stretched into thin streams as gravitational forces win over molecular bonds. Recent findings have begun to reveal what's happening right around supermassive black holes, uncovering the chaotic dance of matter spiraling toward these cosmic drain holes. The Event Horizon Telescope snapped the first direct picture of a black hole's shadow in the galaxy M87, showing a dark shape ringed by ultra-hot, glowing matter. These massive entities influence cosmic evolution on immense scales. Their creation and growth are deeply linked to galaxy birth and the development of large-scale structures across the universe. Figuring out how such gigantic black holes exist challenges our understanding of the universe's limits. Still, even these gravitational titans are minuscule compared to the idea that the universe might be infinite, making our visible chunk just a tiny fraction of the whole. If you zoomed out to the edge of what we can see and peered further, you'd spot another 46 billion light-year stretch of galaxies, stars, and cosmic stuff going on endlessly in every direction. Our observable universe covers only the area light had time to reach us since the Big Bang, 13.8 billion years in the making, forming a spherical boundary centered on Earth. It's not because Earth is special, but simply because we're the viewers. Every spot in the universe has its own center of observation. We can't yet tell if space goes on forever beyond our visible horizon or ends somewhere far, far away. Scientists scratching their heads at the cosmic microwave background radiation and other cosmology findings can't decide if our universe is finite or never-ending. Both ideas have evidence backing them, leaving the question of our universe's real expanse unresolved. If the universe is boundless, it would have endless galaxies, stars, and planets in repeat patterns that occur somewhere, and actually must occur endlessly. On the flip side, some theories suggest the universe might be finite yet unbounded, kind of like Earth's surface. You could keep walking forever without falling off an edge, even though it has a limited area. In this concept, space curves back on itself in ways we can't quite visualize, creating a closed space with a limited volume but no edges. Another line of thought is that our universe is just a bubble in a never-ending inflationary cycle that churns out countless separate cosmic zones. Each of these bubbles might have its own set of physical laws, types of particles, and core constants, making our observable universe just one part of a vast multiverse with endless realities. Whether the universe is infinite or not changes how we think about our place in it. If it's finite, then what we see is a big chunk of the whole pie. But if it's infinite, then even the most massive things we can detect are just a drop in the ocean. Recent pinpoint measurements on the universe's curvature using cosmic microwave background suggest that our universe's space is flat, or pretty close to it. This flatness implies space could be infinite, though it doesn't prove it stretches on beyond what we can observe. Meanwhile, dark energy is making the universe expand ever faster, which affects how much of the universe we can actually see. As this expansion speeds up, light from more and more distant objects won't reach us, eventually putting most of the universe out of sight, even theoretically. Future civilizations might find themselves on lonely cosmic islands as galaxies around them drift beyond view. No clear-cut answer exists about whether the universe is infinite according to current theories. Ideas like string theory and other highbrow physics models come up with different possibilities about the universe's shape and size. But we can't verify any of these with today's tech. The question might just be one of those mysteries we can't fully unravel. Even if the universe is infinite, the part that can affect us is still limited. Since information can't travel faster than light, only events within a certain distance can impact us. This is our causal horizon. With that in mind, the universe we can interact with is contained within this visible, causal bubble. If the universe is infinite, it reshapes our thinking, making even the biggest cosmic forms look like tiny wrinkles in a colossal fabric stretching beyond our grasp. But in our limited view, the oldest remnants of the Big Bang, ancient radiation, give us detailed insights into the universe's beginnings. Back in 1992, the Cosmic Background Explorer satellite created the oldest snapshot available, charting tiny temperature changes in the cosmic microwave background radiation. This image dates back to when the universe was just 380,000 years old. These minuscule temperature variations, just fractions of a degree, trace sound waves in the dense plasma before the first atoms began. It's like time froze when the universe shifted from opaque to see-through, locking in clues about conditions some 13.4 billion years ago. This find earned a Nobel Prize in Physics for being the first real proof supporting the Big Bang theory and cosmic inflation. The temperature shifts lined up with theoretical expectations with mind-blowing accuracy, backing the idea that the universe kicked off in a super-hot dense bang and has been cooling and growing ever since. More than just a confirmation, these ancient patterns reveal the very beginnings of cosmic structure development. Slightly warmer regions in the microwave background are linked to denser areas in the early universe. Over billions of years, these denser spots evolved through gravity to form galaxy clusters, superclusters, and cosmic filaments we see today. The Wilkinson Microwave Anisotropy Probe, and later the Planck satellite, mapped these temperature differences more precisely, uncovering details about the universe's makeup, geometry, and growth. Findings show the universe has the perfect amount of matter and energy to keep space flat, backing up theories of cosmic inflation. Studying the microwave background's polarization patterns sheds light on the conditions of the universe shortly after the Big Bang. These patterns could even uncover gravitational waves from cosmic inflation, giving direct proof of the rapid expansion that shaped the universe's vast structure. The temperature map also limits what we know about dark matter and dark energy based on their impacts on cosmic evolution. The gravitational pull of dark matter affected how sound waves traveled in the early universe. Meanwhile, dark energy's push impacted when cosmic expansion sped up compared to gravitational slowing down. Recent precise measurements point out minor oddities in the microwave background that puzzle standard cosmological models. The southern hemisphere is slightly warmer than its northern counterpart, and there's a noticeable asymmetry that contradicts the expected cosmic uniformity on a large scale. These oddities might mean the observable universe is part of a bigger cosmic structure, or that the inflation process was more complex than simple models suggest. Some alternative ideas propose changes to basic physics or unusual properties of space itself. The cosmic microwave background also provides us the best measurements of the universe's age, expansion rate, and matter content. When combined with other cosmic observations, this ancient radiation offers a detailed history of the universe from its start to now. Future missions aim to observe the microwave background even more closely, possibly spotting primordial gravitational wave signatures or other unusual events from the universe's beginning. Ground-based telescopes search for specific polarization patterns that gravitational waves would leave on this ancient light. The temperature map is humanity's deepest dive into cosmic history, capturing conditions that existed billions of years before Earth came to be. Each measurement adds to understanding fundamental questions about cosmic beginnings, development, and ultimate destiny. These early universe snapshots mark the moment space became clear to light, also highlighting mysterious forces that keep molding cosmic evolution over vast scales and time frames. This ancient radiation serves as both a historical record and a guide to understanding the dynamic forces driving cosmic expansion and structure formation throughout the universe's lifespan. Somewhere out there in intergalactic space, dark energy exerts a repulsive force so strong that it speeds up the universe's expansion, eventually pushing galaxies away faster than light can follow. This mysterious force makes up roughly 68% of all energy in the universe, yet its nature remains a mystery despite years of study. Dark energy acts like a counter-gravity field, growing stronger as space stretches, overpowering the gravitational pull between galaxies and accelerating cosmic expansion. The discovery of dark energy upended fundamental beliefs about the universe's destiny. Before 1998, astronomers thought gravity would eventually slow expansion and might even reverse it, leading to a big crunch where the universe collapses into itself. Instead, findings showed that expansion is speeding up, ensuring the universe will keep growing indefinitely. The latest observations show that the universe is expanding faster, with the space between distant galaxies stretching at a rate of about 70 kilometers for each extra megaparsec of distance. This means galaxies located 10 billion light-years away are cruising from us at speeds nearing a third of light speed purely due to cosmic expansion. Beyond that, expansion can push galaxies apart faster than light itself can travel. And this doesn't break relativity rules, since the galaxies aren't moving super fast through space themselves. It's space that's stretching out. Einstein's speed rules focus on moving through space, not the stretching of space itself. As the universe grew older and larger, the impact of dark energy strengthened. Back in the day, when matter and radiation were thicker, gravity's pull was stronger than dark energy's pushing force. But in the last few billion years, dark energy has taken the wheel in cosmic evolution. What dark energy actually is still baffles physicists. The top theory suggests it's vacuum energy, where empty space has energy thanks to quantum fluctuations. Yet, calculations of this energy's density overshoot what we observe by a whopping factor of 10 to the 120th power, marking one of science's biggest disagreements between theory and what's seen. Other ideas suggest dark energy is a novel kind of field-filling space, akin to the electromagnetic field, but with stranger repulsive qualities. Such fields might shift over time, altering the rates of cosmic expansion as the universe ages. Some scientists think what we see as dark energy might actually come from tweaks to Einstein's general relativity on a cosmic scale. These altered gravity theories propose gravity's pull weakens over vast distances, causing what seems like accelerated expansion without needing bizarre energy factors. The James Webb Space Telescope has recently started testing dark energy models by analyzing how cosmic expansion rates have varied in older periods. If dark energy has morphed over time, the telescope could spot changes in expansion rates from the universe's early days to now. The ultimate fate of a universe led by dark energy hinges on whether this mysterious force stays constant or evolves over time. If dark energy keeps getting stronger, it might eventually pull apart everything, from galaxies to atoms, in a big rip scenario. More likely outcomes suggest dark energy will hold steady, producing a cold, desolate cosmos where galaxies drift apart, slipping beyond each other's viewable edges. Over time, the universe would mainly feature solitary star clusters amidst vast emptiness. Figuring out dark energy remains one of science's toughest nuts to crack, as it impacts the eventual destiny of all existence. Discovering whether the cosmic web will endure for eons or unravel through relentless expansion is key. These universe-wide forces pave the way for a final understanding of just how vast the universe truly is. In January 2025, an international group of astronomers reported the most exact cosmic distance measurement ever made, shaking all previous bounds of how expansive the universe really is. They combined James Webb Space Telescope data with gravitational lensing from ground surveys, achieving a staggering 0.1% accuracy across billions of light years. This precision unearthed systematic flaws in older cosmic measurements that had skewed the cosmic distance framework for ages. The breakthrough came from meticulously studying how light bends around distant galaxy clusters, creating multiple distorted views of background galaxies. By using advanced computational models to analyze these lensing patterns, astronomers can now accurately determine distances to both the lensing clusters and the faraway sources. The updated measurements suggest the observable universe is actually 94.2 billion light-years in diameter, not 93 billion as previously thought. This extra 1.2 billion light-years means a volume increase similar to adding millions of Milky Way-sized regions to the space we can see. More importantly, the improved distance accuracy shows that cosmic expansion has been more uniform over time than previously imagined. Earlier surveys suggested that expansion rates changed a lot during different time periods, but this new data points to a smoother evolution that lines up with simpler cosmological models. The new cosmic inventory suggests there are about 2.1 trillion galaxies within the observable universe, backing up earlier estimates that were based on statistical counts of galaxies. But with better distance measurements, we now see that these galaxies are spread out more evenly across space than we used to think. Perhaps most importantly, this new data gives us the best evidence yet for the idea of a potentially infinite universe. By mapping how galaxy clustering statistics change with distance, the team found patterns strongly supporting the idea of an infinite universe over a finite one. The data indicates that cosmic structures extend far beyond what we can observe, with no hint of any edges. These insights help resolve some long-standing mysteries in cosmology. The so-called Hubble tension between early and late universe expansion measurements disappears when you factor in these corrected distance errors. The apparent clash between cosmic microwave background readings and local distance measurements was down to calibration mistakes, not issues with fundamental physics. This improved precision also affects how we understand dark energy's development through time. The corrections show that dark energy's impact has been surprisingly constant throughout history, backing up theories that suggest it's a fundamental aspect of space itself. Future observations are set to extend these precise measurements even further into space, thanks to next-gen telescopes and better gravitational lensing techniques. Instruments like the Extremely Large Telescope will spot individual stars and galaxies billions of light-years away, giving us new reference points for measuring cosmic distances. The ultimate aim is to chart out cosmic structures across the entire observable universe with extremely high accuracy, building a complete 3D map of galaxy locations and movements throughout cosmic history. This extensive survey could definitively test ideas about cosmic inflation, dark energy development, and the universe's ultimate size. The announcement in January 2025 marks a game-changing moment in our quest to grasp the cosmic scale and structure. For the first time, we're able to measure the universe's size and contents as accurately as we conduct surveys here on Earth, shifting cosmology from a qualitative science to a discipline of precise measurement. These discoveries about cosmic structure push us to face some profound questions about our place in a reality that's far bigger and stranger than our forebears could have imagined. The final conclusion from all these cosmic distance measurements leaves no doubt about our position in an unfathomably vast cosmos that could stretch endlessly beyond everything we'll ever be able to see. As you stand under a sky full of stars, you're gazing out at a universe with over 2 trillion galaxies distributed across 94 billion light-years of observable space, with the real cosmos potentially spreading infinitely beyond the reach of any telescope. The sheer scale is beyond human understanding. If every star in our galaxy were a grain of sand, all the beaches on Earth wouldn't hold them. And yet, the Milky Way is just one galaxy among trillions, each with hundreds of billions of stars. The observable universe contains more stars than there are atoms in every human who has ever lived. This realization pushes us to grapple with one of the most profound insights in human history. We're just a tiny speck in the grand scheme of things. Earth spins around an ordinary star, tucked away in a typical galaxy that's situated in a rather nondescript part of the observable universe. If the universe were limitless, the piece of it that we can observe would basically shrink down to a point so small it disappears. Strangely enough, this cosmic triviality shines a light on humanity's amazing feats. Over a few hundred years, we've managed to figure out the universe's size, age, and how it's made and evolved. Armed with tools we built and math we figured out, we've traced its journey right from the Big Bang on through the birth of galaxies, stars, and planets that could host life. Discovering that we can see galaxies from when the universe was just 5% of its current age shows that human civilization is watching events from over 13 billion years ago. We're like cosmic detectives piecing together the universe's story from ancient light that's been heading our way since long before our solar system took shape. Our findings show that the stuff that makes us up was forged in stars billions of years ago, shot across space by supernovas, and eventually became part of the planets and life we know today. We are literally crafted from recycled stardust, thanks to universal processes that played out long before Earth ever existed. The vastness we've uncovered hints that life might be common all over the universe. With countless galaxies, each boasting billions of potentially life-supporting planets, it's highly unlikely Earth is the only stage where life kicked off. The universe is probably teeming with life, possibly even civilizations far advanced beyond ours. Viewing things through this cosmic lens changes how we view human squabbles and worries. The political lines that split us mean little when seen next to a universe hosting countless other worlds. Our environmental issues, while crucial for us, are just local blips on a planet that's only one among many. Knowing that dark energy rules the universe reveals that most of it is made of stuff we don't get at all. The matter we're familiar with, like the kind that forms stars, planets, and us, makes up less than 5% of the cosmic tally. We're minorities living in a universe run by mysterious forces and unseen matter. Yet, our small cosmic role doesn't take away from the importance of human life. We are the universe trying to understand itself through awareness and scientific exploration. Through humans, the cosmos finds a way to gauge its size, track its history, and ponder its future. The vastness we've uncovered makes Earth special because it's rare. In a space mostly empty, with matter existing as solitary atoms in intergalactic spaces, the rise of complex chemistry, biological evolution, and conscious thought becomes a stellar cosmic triumph. Our measurements of the universe's staggering size lead to a deep realization. We're not separate from the universe we explore, but rather its method for becoming self-aware. Every person who has ever gazed at the stars plays a part in the ongoing mission of reality, trying to understand itself. The final takeaway from these cosmic distances is that size doesn't define significance. In a universe that might stretch infinitely beyond what we can see, conscious beings capable of measuring that infinity, are the most incredible constructs nature has ever put together.